The example I want to do of evaluating line integrals by double integrals using Green's theorem is in fact a very classic example, and we're gonna discuss it from several aspects, and it's also going to lead us to our next topic, which is the topic of conserving fields. But that would be a bit later. So here's the example, classic example. We're going to look at the field f of xy, which is minus y divided by x squared plus y squared. That's the I component, plus x divided by x squared plus y squared, which is the j component. Okay, so this entire thing is p of xy, and this entire thing is q of xy. Good? Now the first thing I want to do, since we're going to be discussing Green's theorem, is find the two relevant partial derivatives that show up in Green's formula. So I want to find dq to dx, and I want to find dp to dy. Okay? So let's do that. What is dq to dx? I want to take the derivative of this thing, thinking of y as fixed and thinking of x as the variable. So I'm going to have to use a quotient rule there. Do you agree? So it's going to be the derivative of the top, which is 1, times the bottom, x squared plus y squared, minus the derivative of the bottom, which is 2x, right? Y is just a constant now, times the top, so 2x squared, divided by the bottom squared. Do you agree that this is dq to dx? Okay? And we can simplify things a bit. We have an x squared here minus 2x squared, so we can write it as y squared minus x squared divided by x squared plus y squared squared. Now let's calculate dp to dy. So it's this, and now I'm taking the derivative with respect to y. So again, it's going to be a product rule. So I'm going to do, a quotient rule. So I'm going to do the derivative of y, which is minus 1, times the bottom, x squared plus y squared, minus the derivative of the bottom, which is 2y, because it's the derivative with respect to y, times the top, minus y. All of this divided by x squared plus y squared squared. Right? Everybody following? Okay. So what do we have here? Here we have minus y squared plus 2y squared, which makes it a plus y squared, minus this x squared. So we get y squared minus x squared divided by x squared plus y squared squared. And now if you observe carefully, you must notice that they're equal. Do you see that? So for this specific example, and this is what makes it the classic example, we just found out that q sub x, the derivative of q with respect to x, is precisely the same as the derivative of p with respect to y. Okay? Therefore, let's take a look again as we pass to the next board. At this board here, Green's formula tells us that the double integral is the integral of dq to dx minus dp to dy. If they're equal, then what's sitting here is one nice big round 0. And therefore this right-hand side is going to be 0. Therefore the integral of the original field f, of which p and q were the components, the line integral of that over any curve is going to be 0. Do you agree? Well, you should agree almost. You're agreeing too easily. So what did I just do? I looked at the formula and said, okay, these two were equal. That was a fair enough calculation. Therefore, this is 0. Therefore, the integral of 0 is 0. These are equal. Therefore, this is 0 for any gamma. Right? No. That's not the issue. The issue is that I just looked at the 5th line of a theorem and ignored the 4 lines preceding it. That's a big no-no in mathematics. Okay? You can't apply a theorem without checking the details. Right? So the details here are that, well, the gamma and d have to be nice, but even if they're nice, the field has to be C1. C1 where? C1 in the domain over which you're integrating. Maybe we should add that. C1, let's add it here, over a region containing, missing some letters here, containing D and its boundary. So containing D, the closure of D. Okay? Is our field, is that field in the classic example, is it C1? Let's look at the field again. Here's the field. This is it. Is this C1? In other words, are P and Q C1 functions? Right. They're almost C1 functions. In fact, they are C1 functions in any domain as long as it doesn't contain the point 0, 0. If it doesn't contain the point 0, 0, then everything is fine. Okay, in any other point, you can find a neighborhood for which these two are, you can calculate the derivatives and they're going to be continuous and everything is going to be fine. The only issue, the only obstacle to being C1 on the entire R2 plane is what happens at 0, 0. And at 0, 0, there's no way to amend this, right? At 0, 0, this is not even defined, let alone continuous, let alone C1. Do you agree? This field is not defined at 0, 0. Does everybody see that? Okay. So back to this board. If we choose a domain that does not contain, if we choose a region that does not contain the origin, then for any d there and any gamma which is its boundary, we can say what we just said. The line integral of that field is going to be 0. But what happens if we take a gamma which encircles the origin, for example? That we're going to have to see, and we will. So, if gamma is anything that does not circle the origin, for example, this thing. This is gamma. If this is gamma, then I can call this D. This is going to be D. Gamma is smooth, positively oriented with respect to D. Pum, 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 pum. Right? Everybody understand why I'm dancing here? Okay, positively oriented with respect to D. Piecewise smooth, simple, closed, planar, everything's good. The double integral, or let's say this, then the integral over the closed curve gamma of this specific f from this example, so this is not just any f, this is our f, the field we're considering in this example, this classical field, is going to be 0 by green. Capital green. Clear?
It's 0 only in using our function.
We're only, throughout this entire clip, f is not a general field, f is that specific field throughout this entire clip. Okay? So over a gamma like this, or any gamma, okay, so let me, because the integral over f dot dr equals the double integral over qx minus py dx dy over d, and this equals the double integral over d of 0. This is because qx equals py for this specific f, and therefore this is 0. And now I have to close these parentheses, and I'm out of board. Clear, everybody? And this is going to be true for any gamma as long as the origin is out of it. Okay? So, true for any gamma, well, any gamma piecewise closed, simple, blah, 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 that does not or let's say for any gamma which is the boundary of D such that away from the origin, let's write, because it's going to be a more delicate issue, we'll discuss it. Away from the origin. Clear? But if the origin is somewhere in there, the theorem fails. The field is not C1, we cannot use the theorem. We're going to have to do something different. Is this clear? Everybody? Okay. So for example, if gamma is, let's say gamma is this, tell me if the theorem works. Oh, this is fun. If this is gamma, will the theorem work? Yeah, no problem. This is going to be the positive orientation. This is going to be the domain. And the theorem holds. So it's really fun to calculate line integrals of this field over various curves. In general, if I would give you a curve and ask you to calculate this line integral, you would freak out. How would you parameterize a curve like this? Right? You didn't see my face. Right? How would you parameterize a curve like this? Completely unclear, right? But because of green, it's 0. I don't care what the curve looks like, as long as the origin is not inside. Do you agree? Does everybody understand? What if the origin is inside? Let's see an example. So let's look at, I'm going to erase this. I just did the most stupid thing and erased the field, which, okay, we'll rewrite it. Okay, so what if gamma is, let's say, the unit circle, or any circle, is a circle x squared plus y squared equals r squared for some r. So now this is the picture. Here's gamma. And I want to calculate the line integral, the work done by a force given by our field, which was, let me just remind you, F was minus y over x squared plus y squared, comma, x over x squared plus y squared. This was F. What is the work done by this force along this curve? Well, there's no green shortcut, right? I can't apply Green's theorem, but I can still calculate line integrals right? That's what we discussed previously. Let's take a peek at this board. I know how to calculate line integrals. This is how I do it, right? I need to parameterize the circle and then calculate this thing and hope that it doesn't come out too terrible, right? Since I know how to parameterize a circle, that's easy. And let's just hope that the calculation is not too nasty, and it's not. So here's the answer. The integral of this f, it's always this f in this clip, over the circle, now gamma is this circle, equals, so what's the parametrization of a circle? That's the unit circle, but here it's a circle of radius r, then it's r cosine t, r sine t, right? So let's write that. R of t, this is the parametrization, is r cosine t, r sine t. This is a good parametrization of the circle, where t ranges between 0 and 2 pi, right? So we're going to have the integral from 0 to 2 pi. And I'm just going to write everything like there. I need p times x prime plus q times y prime dt. So what is p? This is p. This is p. And this is q. Right? This is x. And this is y. So let's write all the details. P evaluated on this. So it's minus y minus r sine t divided by x squared plus y squared, which is what? R squared. This is p. Times x prime. What's x prime? Minus r sine t. So this is x prime, and this is p evaluated on the circle. Good? Plus q evaluated on the circle. So x is r cosine t divided by x squared plus y squared, which is still r squared, times y prime of t, r cosine t. This is q evaluated on the circle, and this is y prime. And then all of this dt. Did everybody understand what just happened, what I just did? Okay, so I'm doing a straightforward, no theorems, straightforward evaluation of a line integral by definition, parametrizing the curve and doing what needs to be done. So what do I get? Minus r times minus r is r squared, divided by r squared is 1. So here I'm just left, in all of this, I'm just left with sine squared. Here, r times r is r squared, divided by r squared is 1. So this is just cosine squared plus sine squared is 1. So all I'm left with is the integral from 0 to 2 pi of 1 dt, beautiful, which is just 2 pi. Do you agree? Okay. So I want to point your attention to two things that just happened. One, the answer is not 0. For gammas which didn't include the origin, for gammas out here, we saw that the answer is 0 because of Green's theorem. But for a gamma that does circle the origin, the answer is not 0. In this example, it's 2 pi. Do you agree? And the second thing that just happened is that it doesn't depend on r. Whether you're doing the work along a tiny little curve around the origin, or you're doing the work along a giant circle around the origin, the total work you'd be doing in moving a bead along this wire, if this is the force, is going to be 2 pi, independent of the radius. Do you see that? Okay, so let's remark does not depend on R and is not 0. Okay, so is the reason for pointing these two facts out clear? Okay. Okay, good. Let's see if we can say more. Okay, so suppose, for example, I want to calculate the work of this force F, which is the physical way of saying the mathematical statement, the line integral, this line integral, but not just on a circle, but on some weird amoeba like we had last time, but that does contain the origin. Okay, so let's do that. So suppose now I want to calculate on a very weird shape like this, but now the origin is going to be in there. So here the origin was here, it was not inside this shape. Now it is going to be inside. Let's see what we can do. So as a preliminary step to that, I'm going to point out the following. Consider a ring that looks like this. Suppose you have two circles centered at the origin, and the domain D is the ring, the domain in between them. So this is now D. And the boundary of D is the union of these two rings. And in order to have it positively oriented, let's call this gamma 1, and gamma 2 is going to be clockwise. This is going to be gamma 2. Good? Clear why this orientation? Left hand. Right? Okay. So I'm still looking at that specific field. Can I apply Green's theorem in this case to this domain D? The answer is yes. The field on this domain D, the field is defined. It's C1. The fact that in the hole inside the ring there's a point where the field is not defined, I don't care about that. Okay, so the theorem does hold. So the integral over gamma, where let's denote gamma is going to be gamma 1 union gamma 2. So gamma is going to be gamma 1 union gamma 2. Okay, the entire boundary of this domain D. So the integral over gamma of f dot dr, integrals are additive. Integrals are additive, so it's the integral over gamma 1 of f dot dr plus the integral over gamma 2 of f dot dr. Right? What's the integral over gamma 1? Gamma 1 is a circle around the origin of some radius, but we just calculated that it doesn't depend on the radius, that this thing is 2 pi. Do you agree? What about gamma 2? Not exactly, almost. Gamma 2 is a circle around the origin, but it's oriented in the negative, it's oriented positively with respect to D, but it has the opposite orientation to the curve for which the work was 2 pi. So what's going to be the work along gamma 2? It's going to be minus 2 pi. Okay? So when we change the orientation of a curve, the work is going to change signs. Okay, we discussed that. So this is going to be minus 2 pi, and therefore along the union of these two curves, we're going to get 0. Do you agree? Okay. Now, this is not very important, what just happened here, but it's the idea I want to pick up and use it in order to calculate. Suppose now that I want to calculate, I'm going to erase this field again, and let's think before that if I'm going to be upset afterwards. No. Okay. So now let's consider, take any amoeba-shaped gamma, as long as it's, of course, planar, piecewise smooth, simple, closed, positively oriented, around the origin. Here's the origin. And here's gamma. Okay? Can I use green? Can't use green. Not if the domain is everything inside here. But just like in that example, so what we want to calculate is the integral over that gamma of our field, of this classic example. What I can do is I can take these scissors, do you see scissors? And cut out a little hole here. Do you see the hole? So this is gone now, no origin. Okay? And I'm going to declare the domain D to be this blob of paint here. But with a hole in the origin. This hole is not contained in D. This is D. So on this domain, can I use Green's theorem? The answer is yes. So let's call this little hole, let's call it gamma 1 and oriented clockwise so that it's positively oriented with respect to our domain. Okay. And now what I can say is that the integral over gamma union gamma 1, gamma is the blue which I was originally interested in, and gamma 1 is the little red hole. This is equal to the double integral of qx minus py over the domain D, which is 0, because qx was equal to py. So here, Green's theorem does hold. Do you agree? Therefore, the integral over the blue amoeba, which I was interested in, gamma of f dot dr, is what? I can write it as this integral, gamma union gamma 1, minus the integral over gamma 1. Because their sum equals this. Do you agree? And what do I know about the first one? It's 0. I just calculated it. Minus, what's the second one? What's the integral of the little red curve of the hole there? Minus 2 pi, because it's oriented clockwise. And it was 2 pi for counterclockwise, so it's minus 2 pi. And therefore, we get 2 pi. Do you agree? Okay. So this is a standard trick for calculating line integrals of curves for which their interior, the domain inside them, is problematic because of the field. Okay? So I hope you noticed throughout that there were two things that played different roles. One was sitting inside the snake, the other was sitting under the snake. One is the domain, the other is the field, the function. Okay? And the theorem has requirements on both. And only when both requirements are satisfied, when there's this compatibility of the field being C1 on the domain, then everything is good. So by playing around a bit with the domain, and this is a painful playing around by making a hole in it, then we can use Green's theorem, and this is a standard idea. Okay? So throughout all the 4 examples we did of this specific field, in all of them, the idea was, when possible, to use Green's theorem to calculate a line integral by means of a double integral. Okay? Questions about these 4 examples? Yes? Here? Yeah. Because throughout this entire clip, it's the same f. And that f satisfied qx equals py. Therefore, this is 0, and therefore the double integral over any domain of this thing is 0. Clear? Okay. So, notice that something interesting happened here. There was this independence, to an extent, there was this independence of the result with respect to the curve. So whenever gamma was sitting out there and not circling the origin, the line integral was 0, no matter what gamma was. Gamma could have been a nice round circle, or gamma could have been a wild, crazy amoeba. Okay? And likewise, if it circles the origin, whether it's a nice circle, small circle, big circle, giant circle, or any amoeba, the answer is 2 pi. Do you agree? Okay? So it's not always 0 or always 2 pi for this example, but it can only be one of those 2 values depending on whether it circles the origin or not. And that's the only thing that factors in. Everything else doesn't matter. That the shape of gamma, this line integral doesn't care about it. Okay? So it's this stability of the line integral with respect to the shape of the curve that we're going to want to give a name. We're going to want to explore fields that have this property that the line integral is really independent of the curve. And what this means is that when you're doing work, right, the line integral of f is the work done by f, right? That's the physical interpretation. The work doesn't really depend on the path you're taking, right? It only depends on very specific data, like does it circle the origin or not? That's it. And that's a very useful thing to know. So if you're really doing physics and you want to move an object from point A to point B, and you know that the work you're going to do doesn't depend on whether you take kind of a path or go in the straight line, that's a good thing to know. Why not go in a straight line, right? So that's going to have a name. It's going to be called a conserving field, and that's the topic we're going to discuss next. So Green's theorem requires proof. That's one thing we didn't do. Depending on time restrictions, maybe we'll add a proof a bit later, and we can always put in the clip in the appropriate place in the lineup of the video course. So, but for now, we're going to just accept the theorem without a proof. The proof takes a while, okay? It's not too sophisticated, and there are some very neat and important ideas in the proof. But for right now, we're going to move on without the proof. I want to give you a little practice homework before we wrap up this one. Calculate without green the line integral of this f over some curve that, let's say, the line integral of f over gamma, this f, the f we're considering in this clip, for gamma, which is maybe, say something like this, maybe like a diamond shaped. You can do other things as well. What do I mean calculate without using green? So this is going to be gamma. Okay, a diamond shape around the origin. What's the answer going to be? It's going to be 2 pi, right? Using green, it's easy to calculate. Drill a hole and do the exact same thing we did here for that weird amoeba, right? But try to do it the straightforward way. By evaluating the actual line integral, you're going to need to parameterize this, okay? And note that this is piecewise smooth, right? It's smooth, 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 so it's piecewise smooth. And you can parameterize each segment separately and do the calculation. It's a bit of practice, but it's easy and it's important in order to get the feeling for calculating line integrals. You're going to have a lot of examples in your homework, but try this one as well. See that it actually comes out to be 2 pi, like we're expecting because of green. Okay? Okay, good.